All right. Now that we've looked at resonance structures, at this point you're probably a bit confused still. We will get lots of practice with this, doing resonance forms and whatnot. Let's just finish up the chapter real quick, short video here, about exceptions to the octet rule. There are certain situations when your central atom will not have an octet, and it turns out that is totally appropriate, and nature says, oh, that is fine. The first thing are fairly weird molecules, odd electron molecules. This molecule right here, NO, nitric oxide, it is a molecule. It does exist. Everything fine there. But when you do the Lewis structure, we find out, okay, nitrogen has 5 valence electrons, oxygen has 6 valence electrons. That's 11 valence electrons. And so when you try to do a Lewis structure here, well, okay, what's our central atom? Well, 2 atoms, so not one can be central, but let's just follow the rules normally. Oxygen is more electronegative than nitrogen, so let's say oxygen is the terminal atom. And you would say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You've got this lone electron. Note, you've got an odd number of electrons. You cannot have all paired up electrons. You can't have it, if there's an odd number, you're always going to have one electron left out. So note, nitrogen does not have its octet, so let's take one of these lone pairs, do this, and that gives us this beast right here as our Lewis structure for nitric oxide. And this is just still not great. Oxygen has its octet, but nitrogen does not have its octet. When we look at nitrogen, it has 1, 2, 3, 4, 5, 6, 7 electrons when we're trying to count its octet. But you realize at this point there's nothing else we can do, because if we took another lone pair to make a triple bond, then nitrogen would have 9 electrons around it extra, and it can't do that. The fact of the matter is, if you're looking at formal charges at this point, you'll see this oxygen has no formal charge and this nitrogen has no formal charge. So even though this nitrogen does not have its octet, in this structure, there's no formal charges, so this is the structure of this beast. There's not going to be a really good Lewis structure that follows all of our rules because we have that one extra electron. But here we've got the lowest formal charges, so this beast right here is our Lewis structure for nitric oxide, this NO molecule. Odd electron molecules are kind of weird. The next thing are incomplete octets. When you look at some of the atoms in the periodic table, especially boron, and right below boron on the table is aluminum, you'll find out that we're going to get some issues. BH3 molecule works. It's a nice molecule. You can buy it. And it's got a problem, because if you count the electrons, hydrogen has 3 electrons, one for each hydrogen. Boron has 3 electrons, that's 6 total electrons. You do with the Lewis structure, and there's 1, 2, 3, 4, 5, 6. There's all of our electrons. Does boron have its octet? No, it does not. Boron does not have its octet. Well, can't we form a double bond to the boron? No, there's no electrons on any of these hydrogens to form a double bond with the boron. So here you have a molecule where boron does not have its octet, but the molecule is fine with that. BH3 does exist. AlH3, aluminum is right under boron, you get the same issue. Interestingly, if you do the Lewis structure for BCl3, and you put all the electrons in there, you find that this is the Lewis structure. Once you've added in all of the electrons, all 24 electrons for BCl3. And we see, okay, does boron have its octet? No, it does not. Boron does not have its octet. Ooh, but couldn't you form a bond between the chlorine and the bromine, a double bond here? Well, you could, but watch what happens when you do that. If you take one of these chlorines, and let's take the top one and form a double bond, Now the boron has its octet, but let's look at formal charges. This boron, 1, 2, 3, 4, boron now has a negative formal charge, and this chlorine has a positive formal charge. Up here, all the formal charges were 0. And so look at these two structures. Which is the better structure? Boron not having its octet and all formal charges being 0, or boron having its octet but chlorine, a much more electronegative atom, having a positive formal charge, and boron, the much less electronegative atom, having the negative formal charge. Most people agree that this is the better Lewis structure because we have fewer formal charges, and we know from the molecule BH3 that boron can handle an incomplete octet. So this would be the better Lewis structure with the incomplete octet for boron, because boron often has incomplete octets. Better than trying to make a double bond here and getting formal charges that just aren't where they should be. The more electronegative atom wants the negative formal charge, not the positive. And the last exception to the octet rule are expanded octets. Check this out. We're going to make the molecule SF6. Sulfur with 6 fluorines on it. Okay, so sulfur hexafluoride. If we count, that has 48 electrons. What's the central atom? Well, fluorine is very electronegative, so we definitely expect sulfur to be the central atom. When we make this molecule, we put the 6 fluorines around the sulfur, we add the 48 electrons. I like to do it in one breath. See if you can do it. Take a deep breath. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. Whew, okay. Got all 48 electrons in there. If we look at this molecule, we see, all right, the fluorines have their octets. If we do the formal charges, we see the fluorine has 0 formal charge because each fluorine has 7 electrons around it when looking at formal charge. The sulfur has 0 formal charge because it's got its 6 electrons, but if we're looking towards octets, the sulfur has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The sulfur has 12 electrons around it. That's a lot more than 8. That's 4 more electrons. Can sulfur break the octet rule? The answer is yes, sulfur can. If we look at the periodic table, it turns out, I have a better periodic table around here. Here's a little bit better. That any of these atoms here as our central atom in the n equals 3, n equals 4 shells can expand their octets. Because recall, if we were to do the electron configuration for sulfur, we would see that it is neon core, 3s2, 3p4. We are in the n equals 3 shell, which means there's 3d electrons available, or 3d orbitals available. We are in n equals 3, the n equals 3 quantum shell. The n equals 3 quantum shell has 3s, 3p, and 3d orbitals. Note from our periodic table that we don't have any electrons in the 3d orbitals. The electron configuration is neon core 3s2, 3p6. We would not get to put electrons in 3d until we're down here somewhere. So we have empty 3d orbitals that can handle the electrons. This sulfur does. So sulfur can expand its octet. Question: what about OF6? Can you make the OF6 molecule? Well, question. Oxygen is right here. Its electron configuration for oxygen is 1s2, 2s2, 2p4. We're in the n equals 2 quantum shell. Does the n equals 2 quantum shell have any d orbitals available? The answer is no. D orbitals do not become available till n equals 3. Therefore, you cannot expand oxygen's octet. OF6 does not exist. Where can you not expand the octet? You cannot expand the octet for any of these guys here. Boron, carbon, oxygen, nitrogen, fluorine. You cannot expand their octets because there's no d orbitals to go into. But any of these guys down here, you can expand these guys' octet because we can get the 3d orbitals, which are over here. We can expand the octet for selenium because the 4d orbitals are available for selenium. So you can have expanded octets as long as you are lower than the second row on the periodic table. And that ends this chapter.